Hello, everybody. Welcome to today's episode of the iCANX talks. Today I will be the moderator. My name is Christian Nijhuis from the University of Twente in the Netherlands. These were the speakers of this month. We had, to begin with this month, Professor Trujillo de Santiago that gave a talk, then Len Yang. Last week, Yuri van der Burgt from Eindhoven University gave a talk. And of course, today, I'm more than happy to be able to introduce HongBo Sun from Tsinghua University to you. So these are the other panel members, Alice, Wei Xiong, and Hugo Duan are the panelists. And let me now introduce first Professor HongBo Sun from Tsinghua University. He received his bachelor and PhD degrees in electronics from Jilin University. He worked as a postdoctoral researcher in Satellite Venture Business Laboratory at the University of Tokushima, Japan, from 1996 to 2000. As an assistant professor in the Department of Applied Physics, Osaka University in Japan, he was promoted in 2004 to full professor at Zhejiang Scholar University. Since 2017, he has been working at Tsinghua University in China. His research interests have been focused on laser precision manufacturing. He is a very prolific publisher with more than 500 papers that have been cited for more than 30,000 times. And he has an age factor, an age index that is already very high and getting very close to even the 100. He is also a big contributor to the community by being an editor-in-chief of Light Science and Applications and deputy editor-in-chief of Photonics, which is also from the Nature Publishing Group. So without further ado, I would like to give the dance floor to HongBo Sun. So I will stop sharing my screen now, and then you can start your lecture.
Okay.
I can see your screen. Yeah, seems to be working fine. So go ahead.
Okay, hello everyone. I'm HongBo Sun from Tsinghua University. My field is femtosecond laser microfabrication. So in this talk, I will introduce you our recent research on how to pursue super resolution in femtosecond laser three-dimensional manufacturing. So I will do my introduction mainly in three aspects. First, I will answer a question: why femtosecond laser is needed for manufacturing? Actually, we already have many very good technology for nanofabrication. For example, lithography is best known for the electronic chips production. The resolution and efficiency are both very high. Also, EBL and FIB, focus ion beam. These technologies give the highest resolution in fabrication, and also we have the nano imprinting and so many technology. Then the question is, since I'm doing the femtosecond laser fabrication, why we need such an additional technology for fabrication? Then to start, to give a conclusion, we have to analyze what is the shortcoming of the currently available technology, including these ones. For fabrication, we have to couple energy from the fabrication tool to the materials. So for all this conventional technology, for the energy coupling, we have to make the tool contact with the materials to be fabricated. So for example, either this is a tip, a physical tip, or a focused particle beam. In either case, we need the tip of the tools should contact with the materials. It means the interaction, also the energy coupling always occurs at the contacting point. So contacting point is simultaneously the interaction point, also the energy coupling point. This means all this technology, by this technology, we can do only planar processing or surface processing. So this is the limit of all this conventional technology. So, but what we expect for a new technology, we need a three-dimensional nano processing tool. How to do three-dimensional nanofabrication? For doing this, we have to first purposely choose the laser wavelengths to avoid material absorption. For example, generally the material absorbed at visible and UV. Then we choose the laser wavelengths at near infrared. Then the laser can penetrate into the materials without power loss. So this is the first requirement to do 3D. We treat the laser as a magnetic wave, and then we just avoid material absorption. We can focus the laser into materials. But this is first point. We realize the three-dimensional focusing, and then we can do freeze three-dimensional scanning. But the immediate question is, for the fabrication, we need energy coupling, we need the laser should damage materials. Since we have no absorption, how we achieve this point? The answer is we have to rely on the nonlinear effect, generally the multi-photon absorption. It means the electrons in materials, they should simultaneously absorb 2 or more than 2 photons to accumulate enough energy for the electrons jumping from the fundamental level to the excited level. So it means nonlinear process. Also, in physics, it's actually multi-body effect. So to realize this multi-body effect, we have to make a very high photon fluence. For doing this, actually, we do 2 things. One is to focus the laser in spatial domain. It means we have to use the high AA focusing lens to focus the laser to a very tiny spot. This is in the spatial domain. And in time domain, how to accumulate a very high photon fluence? The answer is we should use femtosecond laser. For femtosecond laser, actually, it's a kind of pulse laser. In the pulse existence, the duration, the transient power is very high. It's also a kind of focusing, but in time domain. By doing this, we can accumulate very high photon fluence at focus spot. Then the nonlinear effects or multi-body effect may occur, not very difficult. So by doing these 2 points, first we choose a wavelength to avoid linear absorption. Then we focus the laser to excite material using the nonlinear effect. Then we realize the world first real 3D fabrication technology. The tool of fabrication can penetrate into materials and to get the nanoscale features of fabrication. This is the unique point of the femtosecond laser fabrication. So 3D is the most important feature of this technology. Additional merit is for this femtosecond laser fabrication, we can do 3D. In addition, we can use it to process hard processing materials. The reason is the transient power is very high. Then we can do a very simple analysis. The question is, how much is the transient power if we emit 1 milliwatt energy in 1 femtosecond? So the answer is 10 to 12 power watt. So this is at the same level of the total power of the electric plants all over the world. Very high transient power. Please pay attention. It is not energy, but the power. The transient power is very high. It means the field strength is also very strong. we know the light intensity is I, and it's related power by the power divided by the area. So the trended power divided by the trended power, then we have the light intensity. Then this high power is directly related to a optoelectric field. The strength reach 10 to 10 watts per meter level. It's a very high, very strong field. We know what is material. Material, actually, they are combined together by the actually electrostatic force, and the corresponding field stress is only 10 to 8 power watts per meter. What it means? It means we exert to the material a very strong external field. This field is almost 2 order or even higher, stronger than the internal field. It means if we exert the laser into the materials, it can destroy the chemical bond in materials easily, no matter what the material is, including diamond, sapphire, quartz, and ceramics. So this is the second unique merit of the femtosecond laser fabrication. It could be applied to almost any materials, even they are hard processing or even they are soft. So if we compare our technology with the currently more very popular technology, we have the unique merit. For example, compare with lithography, it's applicable only to photoresist and nanoprinting, soft material, and this needs metal. But in our case, the femtosecond laser, since the field strength is very strong, it can damage almost any materials. So this is the second unique merit of the femtosecond laser fabrication. Now I give you one example how we use the femtosecond laser to do 3D fabrication. Here is a optical glue. Generally, we paste the glue to the cover glass, to the glass. Then we shine the glass to the sunshine. Then under this light irradiation, the chemical reaction occurs, and the small molecule. Actually, this photopolymer, the original status is liquid. They consist of small molecules. But once they are excited by the sunshine, by light, and the chemical reaction occurs, the small molecule can become the radical. The radical, actually, the chemically very active. They will be combined together, and step by step, the macromolecule will be formed. The macromolecule, they are not easy to move spatially, and then the material status becomes to solid. This is the general process. When we expose, we solidify the photopolymer. But in our case, we don't use the UV irradiation. We don't use the visible, but we use the near-infrared laser. Then we can focus the laser into the material without power loss. And then we can control the light intensity at the focus spot so that the focus spot the material can be solidified by the matter photon absorption. Then if we do the 3-dimensional scanning, following the scanning the locus, the material will solidified into such shape, almost any CD designed shape. If we wash out the unsolidified polymer, the liquid part, then we can get this 3-dimensional skeleton. This is actually the basic principle. We use the femtosecond laser to do the 3D fabrication. Certainly, here the example is the photopolymer, but we can imagine we can do a very similar thing in glass, in the sapphire, in many other transparent materials. We focus the laser to do 3D scanning. The laser focus spot exposed region, the material performance will be changed. So the principle is very similar. Now here is the work I did more than 20 years ago, and a macro boom. And the result was published in Nature And actually, the boot size is similar to the blood cell size. The length actually is only 10 micrometer. The height is 7. At that moment, we claim the spatial resolution is 120 nanometer. So far, we already improve the resolution to something like 7 nanometer. Later, I will give you the detailed introduction. So this is the basic principle, how we do the three-dimensional nano fabrication. Okay, here is the macro boot compared with the human hair. You can see the boot size is much more smaller. Okay, since we already introduced the femtosecond laser microfabrication is unique. And for example, I give you example, how we use the technology to process the special materials. Here is the diamond, the sapphire, quartz, lithium niobate oxide, silicon metal. We can use so many different forms material to make them into delicate three-dimensional structures. And you can imagine a silicon structure of this form, but for sapphire, it's really very difficult. And here is the quartz, three-dimensional, actually it's a sphere structure. This is the example of special materials. Also here, the example of special structures. All these structures are actually real three-dimensional structure. For some of them, certainly you can do the similar structure using the multi-time photolithography. But you know, if we use the multi-time photolithography, the cost and the failure probability will increase with the times exponentially. But for the laser fabrication, the complexity increase of the structure does not mean the fabrication becomes difficult, because the fabrication always follows the very same fluence. We first design the structure using the CD program, then we control the scanning using the laser scanning with a shutter. So with the shutter on off, we can control in different layers, different region will be exposed or not exposed. So then you can understand why the structure becomes complicated, but the fabrication is the same difficulty. The difficulty does not increase. It means the technology is a intrinsic three-dimensional processing technology. And then I can show you the technology is very useful. We already use it to produce the component and devices in different fields, in optics, electronics, micromechanics, microfluidics, and so many different fields. Once certainly when we choose a topic, always want to consider whether such a fabrication problem could be solved by the photolithography. If it's possible, then we don't try the femtosecond laser, because our technology is the resolution could be very high, but the efficiency is relatively low compared with the nanoprinting and the photolithography. We know our technology, the merit is 3D, it has processing materials. Then if the difficulty meets these 2 points, then we will choose the challenge. So then now I already introduced you what is the femtosecond laser nanofabrication and what is merit. Then our nature question is, for 3D, there's no problem. How about the resolution? Since always we use the resolution to evaluate the fabrication standard. For the photolithography, we need one generation is the 22 nanometer, 14, 7, 5, 3 nanometer. They are in different generations. So for the femtosecond laser fabrication, how we improve the spectral resolution and what is the best level? I will answer these questions. The resolution is the central problem for imaging, also for the manufacturing. And in order to improve the resolution, we should can we borrow some technologies from imaging? This is certainly the starting point of our consideration. We know in the year of 2014, Nobel Chemistry Award is awarded to the three famous opticians for their work on development of the super result fluorescence microscopy. You know their technology, but the technologies are not applicable to solid materials. For example, they always dope the special materials to the some solutions. But for the solid material fabrication, you cannot dope any quantum dot or dye into sapphire, into glass. This is possible. This is the first point. We cannot borrow their technology for our purpose. Second is for the fabrication, we always need a very strong excitation to materials. For imaging, the excitation is always reversible. And after the excited electrons release energy, they recover to their original materials, and the material will be recovered. But for fabrication, we have to remove the atoms from the materials. It's called fabrication. So it means very strong fabrication. For such a strong excitation to realize a very small volume, very high spatial resolution, the difficulty is much more larger. Then we consider in the optical field, do we have any super resolution technology? The answer is yes. Near field optics, they have the super resolution technology. So what is near field optics? We know when we illuminate light into a small particle or a small hole, and following the material distribution, we have such a field. This field is a decayed field, and they are created following the surface physical protrusion. So since when the optical electric field exposed the material, the positive part is not movable, but the negative part, the electric, they are movable. Then after the moving, we will have a dipole like this. This dipole leads to the optical near field. So it means the optical near field can carry the high spatial frequency information exactly the same as the material, as the material surface. But this is by this way we have the super resolution. But unfortunately, this very high super resolution, they are near field. They cannot propagate to far field. So it means for the price we achieve the super resolution is we lose the propagation property of the light field. So then we will consider, is it possible we will preserve the three-dimensional scanning freedom? In the meantime, we have the super resolution. Actually, this is a very crazy idea, but actually we already found the solution. Actually, the solution is we found if we focus the femtosecond laser inside the material, no matter deep or shallow, we can have this kind of holes. You know, if we have shine the hole with light, we will have this kind of near field, as I told you. This near field, they will decay rapidly within generally 10 nanometers. If the hole size is very large, these two sides near field, they have no relation. They don't interact with each other. But once we reduce the hole size smaller than 20 nanometer, or even smaller than 10 nanometer, It means this two near field, they will actually interfere with each other. And the interference result is the local light field strength will become much more stronger, even can become 1 order stronger than the initial incident light field. Okay, this is a very good message for fabrication. It means if we use this small hole, they initiate near field. We can do very high precision fabrication. In the meantime, the fabrication actually is possible because the local field is very strong. So this is, since the small hole can be produced in any position, in 3D inside the materials. It means that this near field fabrication principle can be applied to the random 3D. We have the freedom of 3D-dimensional scanning. We have the super resolution. So this is the example how we use the technology to make the single line. They are very narrow. And actually, what we demonstrate here is 15 nanometer. Actually, in the very new, very latest experiment, we already realized the 7 nanometer spatial resolution. So this is the 3D fabrication, and the rest, the fabrication accuracy is very high. Till the level of 7 nanometer, it means this is a very good technology. So we named the technology OFIB. The full name is optical far field induced near field breakdown. So in abbreviation, we call it optical FIB. You know, the FIB, the original meaning is focused ion beam. So we use such a very similar name means we have the very similar capability. But in our case, we don't use the very high vacuum to caution the ion beam. But for the fabrication and resolution, actually our level is very comparable with the real FIB. Actually, in FIB, they can have nanometer level resolution, but we also we can a little bit worse, but already comparable. So this is the what is OFIB. Certainly, I introduced here. You may ask, since the usage of the optical FIB is dependent on the creation of the seed. But the seed, the shape, and the size are randomly produced, whether they will affect the fabrication. Actually, our answer is no. We found a self-regulation effect. Self-regulation means no matter the original seed hole size is larger or smaller, the resultant line width is dependent, is not affected by the original seed shape and size. Actually, the reason is simple. You can, if the original hole size is larger, it means this two near field, they overlap the smaller. It means the interfered the field, the strength is also weak. It means they produced the weak damage to materials. And on the contrary, if the original hole size is smaller, then it means it will lead to stronger the near field. It means the fabrication will lead to a larger damage area. So as a result, the line width will be determined by the incident laser intensity, certainly related to the laser wavelength. So, but they have no relation with the initial hole size and the shape. Certainly, for this fabrication, we should always control the light polarization direction should be perpendicular to the scanning direction. So, and also if we if we change the polarization, then the hole will be propagate always perpendicular to this. I will give you the example. And here we use this OFIB effect to do the very deep cutting. In this case, we have the material, we have the sapphire sheet. In this case, the width of the single sheet is only 150 nanometer in width, very narrow. You know, we can use other technology. If we use the FIB, we can cut it to the smaller width, but we cannot do the cutting to very deep. But in our case, the width can be several tenths of nanometer in width, and the depth could reach 1 millimeter. It means aspect ratio is more than 10,000. So very powerful, very useful technology. And here you can see from a transparent material sheet, we can cut to such this many identical the cubic. Certainly, we can cut to form other shape, small size the optical component, and the surface quality is something like actually the roughness is less than 10 nanometer. Very good quality. As I introduce you here, you know, the very high nano feature production is not because we focus the laser to very small size, but it's depend on the existence of the seed. Then it means for the parallel fabrication, we don't need the multi-head to, we don't need the multi laser beam. And if we produce the multi-seed here, no matter the seed is produced by laser or produced by FIB or other technology, once we have such a the seed array, we use a wide field irradiation. We can produce the rapidly produce the many this kind of nano features. And here is the example. Next, I give you the movie. You can see how the nano feature is produced rapidly in a very efficient way. Here is the seed. So Generally for nanofabrication, the requirement of the spatial resolution and the efficiency is always contradicts with each other. If the spatial resolution is high, then naturally you have the low efficiency. But in our case, we use the OFIB. We get both simultaneously the high efficiency and high spatial resolution. And then we can have the if we make the optical femtosecond laser optical brush, we can produce the very high spatial resolution structure and with a very high efficiency. Here is the example how we use the technology to produce the industrially useful devices and a black body. Generally, the black body was produced by painting, but the paint is easy to evaporate and they're easy to be damaged. But in our case, here you see the edge is copper, but in the inside the region, the black region, they chemically consist only copper. But why because the color is changed due to actually its kind of structure color, and due to the laser brushed macro nano complex the structure. They absorb the light of different wavelengths. Then after this kind of optical painting, we get a very good, very high level black body. They are very useful devices for the near infrared application. So this is certainly this is the first example how we improve the spatial resolution and how we use the technology. The second is we use the plasmonic nanoprinting technology to create the nanostructure also with very high efficiency. We know if we couple the light into the metal surface, then we can launch the surface plasmon. Then the surface plasmon wavelength will be much shorter than the laser wavelength. But for metal, certainly there's no problem. We have very high intensity of free electrons. But for the electronics, how we obtain, if we want to do the fabrication using femtosecond laser, how we achieve such a high intensity free electrons? The answer is the femtosecond laser high excitation. Because the intensity of the light is very strong, the transient high excitation can produce the very high intensity transient electrons. It means any materials, even if they are de-electrized upon the laser excitation, transiently the surface layer becomes metal. So then due to the existence of such a transient metal layer, we can couple the laser into the surface and we convert the light wave to the SPP wave. Then we control the light intensity. We can brush the nanostructures with very high efficiency. And in this case, 8 centimeter wafer of silicon, we can produce this kind of structure within several minutes. The efficiency is also very high. The last question is, we already improved the spatial resolution to 7 nanometer. Then you may ask, what is the limit? To answer this question, we analyze what is the possible limit. First, to achieve the very high spatial resolution, we already use the multi-photon effect. Here, the yellow part is actually the light intensity, and the real part means the second power of the light intensity, and here is the third power. Because the multi-photon effect is always related to the high order power of the light intensity. It means once we use this effect, the voxel size, also the spatial resolution will be improved. This is the multi-photon effect. Second is the threshold effect. It means it's also a kind of nonlinear effect. It means the laser damaging area is not always follow the laser focus spot size. There exists a threshold. Above the threshold, we have the damaging, and below the material will be recovered after the light excitation. Then actually, if we reduce the light intensity, we can reduce to the damaged area to much smaller than the area of the optical diffraction limit. Then we may imagine if we infinitely reduce the light intensity, this Gaussian beam shape, to make it approach to the threshold level, whether we can choose a particular atoms at the geometric center to excite it, then it means the single atom accuracy of fabrication. So our answer is no, it's not possible to make the fabrication resolution lower than to the single atom level. The reason is when we reduce the light intensity to a certain degree, actually the energy difference between the center part and the edge part becomes smaller than the random fluctuation energy. Actually, this is introduced by the quantum static effect. So in this, it means when we reduce the focus spot to a certain smaller area, and then the laser fabrication, the damage will occur inside inside the area, but in which atoms we don't know. It's random. So this it means we already improved the spatial resolution from the conventional optical diffraction limit to the quantum limit. We know it's small, but in this small area, we cannot tell you which atom will be excited and escape from the system. And we use such an effect, we can produce this kind of single atom very small size damage. And we measure the damage area size is something like smaller than 5 nanometer. It means we know the damage within such small range, but we don't know whether it's at the center or at the surrounding region. But anyway, it's already a close to the atom level fabrication. We use such a high level fabrication capability to produce the very small size, the single photon source. Actually, the single photon source, these are related to the actual single atom defect. And here is the geometrical shape of the single atom damage. And here you can see when we reduce the light intensity to a region to here the level, actually from the spectrum, the second order correlation measurement, the G2 value is already becomes very small, smaller than 0.02. It means that they are very high quality, the single photon source. And then we actually choose a single source and package the source with a laser diode. Then we get the turnkey single photon sources. They are very useful in the quantum application. So then in this part, I answer what is the limit we can do the laser fabrication. And the answer is the quantum limit, several nanometer. And in the next part, I will introduce you how we use this very high speed resolution to do the useful devices. And I will give you the two examples. One is the two photon induced photopolymerization, another the devices inside the glass. Okay, first also for the two-photon polymerization. Conventionally, if we use the photopolymer, we will have the three-dimensional structure. Their shape could be very good. But for any useful devices, the shape is not enough. We should have the function. For example, the electronic conductivity, the fluorescent emission. For this kind of functions, we generally dope the nanoparticle into the photopolymer. Then we will have a problem. And we know the photopolymer is the structure component and the nanoparticle is the functional component. If the structural component, the concentration is high, then it means for the prototyping for the structure formation becomes easier. And but for the from the function point of view, they are not good. If we increase the nanoparticle concentration, the three-dimensional shaping becomes difficult and the function may be good. And we have to do the compromise, but it means from the structural point of view or from the function point of view, both are not perfect because the total concentration for the two composition is 100%. And for each of them, it's almost not possible to reach 100%. And actually, our dream is for each component, we can realize the 100% percentage. Actually, we found the solution. In our strategy, we directly use the nanoparticle. We don't use any photopolymer. And we introduce some ligand as a surface. They are very small molecules. They consist only 2 or 3 units of the saturated chemical bond. Then if we excite the semiconductor, the nanoparticle, then the hole and electrons they will produce, they can excite the surface ligand. And then if the 2 nanoparticles, they are near sufficiently, and the 2 nanoparticles will be immediately adhered together. In this case, actually, the 2 nanoparticles, they are contact and bonded chemically. It means in this case, the nanoparticle, they are the functional component, but the structure will be produced by the nanoparticle directly connection, and this connection is chemical bond. It means they are also the structural component. So it means by using this photo-excited chemical bonding strategy, we can realize both they are the functional component and the structural component, the both concentration are 100%. So actually they are the same thing, they are same particle. So this is in this case, we don't use any photopolymer, but we use only the semiconductor nanoparticle. We can do three-dimensional fabrication. And here is the movie to illustrate the strategy. Okay, here you can see we can use the different nanoparticle, and that gives different emission color. The emission efficiency is very high. It means their function was not damaged by the laser bonding. And certainly we can do very good shape, the three-dimensional structure. Actually, just to see the surface, you can see they are very similar to the photopolymer structure, but in our case, they consist of almost pure nanoparticle. The concentration is almost 100%. So this is also in the same sequence of fabrication, we can sequentially use different nanoparticle. That means we can combine different nanoparticle in one structure. Okay, this is the first step. We can excite the semiconductor nanoparticle and combine and assemble them into 3 dimensions. But our dream is we wish our technology is not limited to the semiconductor. We wish for any inorganic nanoparticle, we can do the very similar thing. Then the key point is whether we can develop a new type of the chemical ligand. Then the answer is the nitrogen radicals. So then we collaborate with our chemist and then develop this kind of surface functional group. They are easily adhere to almost any material surface, and then as not following the very similar strategy, you can see we succeed in almost many different types of the inorganic nanoparticles. We realize the 3D fabrication using this component. So far, we already succeed in almost any in the inorganic nanoparticle, including semiconductor or the electric. We can assemble them into 3 dimensions. So this is the first example, how we use the super resolution technology to do useful 3D structure. Certainly with OFIB, this kind of technologies, we already use them in this 3D fabrication. So the second example is for the transparent materials, for example, how we do use this super resolution to do useful devices. Then we start the analysis from the fiber, how fiber guiding the light. So Charles Kun-Gao, he proposed using the glass fiber to guide the light. Actually, in his age, his proposal is certainly purified the fiber core to reduce the propagation loss. So certainly the more fundamental principle is we should control the core layer, the refractive index should be a little bit higher than the surrounding. Then due to the totally internal reflection, the laser, once they are introduced inside the core layer, they will be confined into the core layer to propagate inside the fiber. This is the basic idea. Certainly, we can fabricate using the semiconductor technology to make this kind of fiber-like structure into two dimensions. And the semiconductor technology, we can design, and using the different layer deposition technology, we can make this two-dimensional road-like structure. And all of them can guide light into different direction. But our dream is, can we do the similar thing into 3 dimensions? Since we can focus light and modify the material performance and in different level, and we can scan the material in this kind of shape, in order to make them guiding the light, we can do two things. First, we should reduce the scattering or the absorption in the laser retin part. The second is we should control the refractive index of the laser retin region, so that the refractive index in the laser retin part is a little bit higher than the surrounding. If we can do these 2 points, then it's possible to get the light into 3 dimension. And here is the answer. Actually, in our case, we for the shape control, the resolution we realize is 10 nanometer. For the refract index control, the resolution is 0.01%, very high. Then we write the 3-dimensional waveguide array, and we realize the photon propagation and even the very high precision manipulation. It's become possible. And also here is another photonic chip. We use the quantum source. Then we do the calculation. In this case, the depth of our writing is already 1.5 millimeter. It's the real 3-dimensional structure. So it means for 3-dimensional structure is also possible. And we already use this 3-dimensional waveguide array for the quantum radar for microwave detection based on the Rydberg atoms. It's a kind of very useful industrial application. So for conclusion, I introduce you a new technology, femtosecond laser manufacturing. The first important feature of this technology is it's a 3D technology. And the second unique feature is it could be applicable to different materials. Certainly, we propose several new principles to improve the fabrication spatial resolution. One is the optical FIB. The second is photon-excited chemical bonding. This is for nanoparticle. This is for cutting. Certainly, it's applicable for the waveguide writing. And the future technology, certainly we can use the femtosecond laser for the very high precision cutting and drilling, but that is not the most useful occasion. The most useful occasion is the last example, 3-dimensional photonic chips, particularly quantum chip. So thank you very much for the kind of attention.
Thank you very much for a very exciting talk, very beautiful. Let me now start sharing the screen so I can introduce the other panel members. So today's panelists are Duan and Xiong and Alice, but let me first introduce Professor Duan. He received his bachelor and PhD degrees from the University of Lanzhou in China in physics. He also worked as a researcher at the Institute of Electrical Engineering at the Chinese Academy of Sciences. From 2008 to 2012, he was a visiting student at MIST and then a research scientist at H-Star in Singapore. And that's where we met each other quite frequently. It was very nice. Then in 2012, he joined Hunan University as a full professor, and he set up there a new laboratory on micro-nano fabrication. His current research interests include extreme micro-nano manufacturing towards ultra-small scales and its applications. Our next panelist is Professor Wei Xiong. He is currently a professor at the Wuhan National Laboratory for Optoelectronics. He currently also serves as the Executive Director of Laser Science and Technology Research Department, same institute. He has received several awards, including the Best Paper Award at the International Conference of Laser Institute of America and of the Optoelectronic Advanced Journals. He is also serving often as chairs at international conferences, but maybe most notably is that he also really contributes in other ways to the community, and he holds editorial board memberships at the International Journal of Extreme Manufacturing, Chinese Journals of Lasers, and Frontiers of Optoelectronics. And his research interests include ultra-fast laser-induced synthesis, assembly and 3D structuring of nanomaterials. Well, Alice doesn't receive any introduction. Everybody knows her as the founder of this platform of iCANX. So let's start with maybe now the discussion part. So I would like to ask Wei Xiong to open a discussion.
Okay, Yeah, thanks, Christian. And first of all, I would like to give my impression about Professor HongBo Sun's talk. And it's a very wonderful talk. And I think this today's impressive talk talking about the nanoscale, the femtosecond laser manufacturing capability based on the especially the optical FIB like effects. It's a really fantastic idea. And I think it opens the door towards the scalable nano manufacturing using light field energy. So it's very impressive. And my question is, for Professor Sun, do you know, could you comment about what's the requirement for the femtosecond laser beam, the sources? So for example, the laser pulse duration or wavelength or repetition ratio to influence the quality and influence the machining efficiency of the fabrication. So could you give us some comments about the laser sources?
Okay, very good question. Actually, generally for the laser fabrication for 3D, as I mentioned, we need the laser penetrate into materials. So, but actually this laser penetration or the transparency, not really a very strict requirement. Material is always transparent, but the only difference is actually the wavelength. Even for wood, for the chair, for the materials surrounding us, the actual electronic wave may be transparent. If we choose a suitable wavelength, they can be penetrated into, and we can use the very similar principle to do 3D fabrication. So this is the first answer. The second is about laser pulse duration. It's depend on materials. For example, for the glass fabrication, it's not always the shorter the better, because sometimes we know the femtosecond laser is known as a cool tool or the cool processing process. But for the waveguide fabrication, we need kind of annealing effect. So if the laser pulse duration is too short, for example, shorter than 100 femtosecond laser, then we have no this annealing. It's not good. So in our experience, maybe 300 femtosecond laser is good. In that level, the field is suitably stronger, and annealing can be can be well done to some degree. So this is for glass. For sapphire and for diamond, for different materials, we should always purposely to consider the characteristics of the material, then choose the suitable laser pulse and pulse width. Okay.
Okay, thank you.
Sure.
So I have another question. So so you demonstrate a very nice result about femtosecond laser machining about hard and brittle materials. And how about can we use such kind of optical near field effect in the like a softer material, for example, like polymer or something, even in the two photon polymerization? Can we use a similar like near field idea to further increase the spatial resolution? I just do you have any like comments or about
actually
for addictive nano manufacturing?
Yes, actually is possible, but we have to consider for soft materials, once we produce the very small hole, which could be used for the seed, but they can be self-cured. So this may be the problem. But our nature is we don't always need a small hole. If we actually small particle is also possible. The only difference is the near field occurs at different side, and maybe they are. I think if we produce some positive point. It means the refracting index in the laser center, they are become larger than the surrounding. In that case, also we have the near field. Theoretically, it's possible to use the technology to the soft matter, even if we are considering for imaging, this effect may work, because once we a little bit damage the material, then we have the near field, the local intensity or the excitation becomes stronger. Then it may be very similar to the the effect very similar to the fabrication. But so far we have no demonstration. If someone are interested in, you may try. I believe we use the OFIB effect, we can do imaging. Okay, thank you.
Thank you. Thank you for wonderful.
Yeah, before we go to the next panelist, I also received a question from the audience, from Lin Lin. Does printing precursor need to be transparent, or will it be a problem if we mix it with magnetic nanoparticles?
Give us more, please.
Does the printing precursor need to be transparent, or can it be mixed with magnetic particles, for instance?
Actually, we need somehow, if the structure is actually, if the structure is small, then the transparent is not a big problem. But if we do a very thick structure, then we need some very good transparency. Yes.
Yeah, exactly. Yeah, thank you. So then let's move on to the next panelist, Professor Duan.
Okay, thanks, Chris. Also, thank you, Professor Sui. Very wonderful talk. So I'm very impressed by a lot of applications realized by femtosecond laser, including optical FRB, further excited chemical bonding, or 3D photonic chips. And also the 3D photonic chips are the most exciting. So I also have a lot of several questions. The first one is, so Professor, you just demonstrated a lot of applications which can only be realized by femtosecond laser. In your opinion, which commercial application will be first realized by two-photon or nonlinear processes by two-photon polymerization? This is my first question.
Okay. Actually, here I didn't mention more examples. Actually, we already set up some small company. They sell the much more types of the advanced optical devices. Most of them consist of the transparent materials. For example, special gratings and some special even MCP. And also we have the example in the application for cutting and drilling. And actually, the femtosecond laser in 20 years ago, when I just started this kind of technology, we see it's kind of play toy, but in these days they are becomes very, very useful. And you mentioned about the two-photon polymerization. Indeed, we for the prototyping of some physical model, chemical model, it's possible. But for industrial application, I have no idea. Sorry.
Okay. Thanks. Yeah. Maybe need more explorations. Okay, this is my first question. The second question is for example, still for industry or commercial applications, how to reduce the cost of this process? Or for example, is it possible to do this use continuous laser, or will materials innovation to reduce the threshold of nonlinear process?
Okay, actually, for applications, we should consider two types of materials. The first type is, for example, the nanoparticle type. In this case, we need the solid 3D-dimensional structure, which are with a very high spatial resolution. In this case, we should consider the function, what kind of function we need for fluorescence emission or for the magnetic. In this case, we need a specially chemically synthesized nanoparticle. This is the first point for pushing forward the application. We need chemical synthesis. The second type of application is for example, for cutting, drilling, or for this kind of application, the material you cannot damage. You cannot change the materials. It's not allowed. In this case, we have to consider how to improve the optical technology, how to control the light field to improve the spatial resolution and efficiency. So this is from material point of view. It means the two types of circumstances. And from the laser point of view, nowadays the laser, femtosecond laser, is already actually very cheap. Actually, is the only requirement we need is the single pulse energy should be sufficiently high. For example, 20 microjoule per pulse is already enough. Then under this condition, we should improve the repetition rate. It means that we can do very fast scanning. If the scanning speed can improve by one order, it means the cost of fabrication will be reduced by one order. So this is the requirement we have to the femtosecond laser field. Okay, thank you.
Okay, thanks. So I just mentioned the 3D photonic chips are the most exciting application, I think. So do your research team have tried to use this method to develop some elements, optical elements or devices for optical diffractive neural networks for optical optical computing, such kind of stuff?
Yes, this is a very promising work, very promising direction. We actually have some unique merit. If you do this, you use the multi-level, the deep level, the neural network. You have to align the optical component, many layers. But in our case, we can do the design, and in one run fabrication, one scanning, we can make the 10-layer devices. We don't need additional alignment. They work perfectly. So this is the merit. We are doing this. Thank you.
Okay, thanks. Yeah, we may have some more collaborations in the future. Okay. Thanks.
Okay, thank you.
Okay, this is one more question, Chris.
Yeah, thanks. Yeah, but let me jump in. I'm also a bit curious about the possibilities of this technology. I think one of the reasons why traditional photolithography is so widely used is because it is compatible with so many different types of materials and post-processing steps. So once you have fabricated the initial structures, you can repeat to make complicated device architectures. So how compatible is this technology with other forms of fabrication techniques to create complex architectures?
Actually, for 3D fabrication, this is the only technology we have. The other technology, you can do very high spatial resolution, but for 3D, actually, it's almost not possible. Also, for the hard processing materials, this is the only technology. But in the future, actually, for the parallel processing, we have some problem because the fabrication is a nonlinear process. It's a very sensitively depend on the light intensity, the pulse duration changes. If we split one beam into 10, for example, the very tiny difference, very small difference in their light intensity, or in the pulse duration, the fabrication results are different. So this is the very serious problem. For the general CW light fabrication, we have no. We just control the exposure time and the light intensity. We can get identical structure. But in femtosecond laser case, it's so difficult to get the same structure. Even we already think the 10 beam are very similar. All the parameter is the same, but what we see is the results are different. So that's the problem.
Yeah.
Okay.
Wow. But maybe because of its sensitivity, that creates in the future also new possibilities. Yeah.
Yeah, nonlinear sensitivity. Yeah.
So maybe we can move on to Alice.
Yes. Great job. Yeah, I know HongBo almost 20 years, but yeah, every year I see your new results, so very exciting. So I have a question. So HongBo, what's next step? So for your technology, you move to like applications for the kind of photonic chips, or you move to fundamental technologies in the future. What's in your mind?
Okay, actually, what's in my mind is in the fundamental research. I'm interested in doing two things. One is about the neural network, as mentioned by Professor Duan. This is very powerful. We can do the very fast parallel calculation. In the NVIDIA, the A100 chip, 90% of the calculation actually is the vector calculation. We are consider how to separate this kind of task from electronic to the optical. Then we do we combine the electric function to the optical function. This is one dream. Another is the quantum chip. We are trying to do the color center chip and the iron chip, iron chip, and also the neutral atom chips. By doing this kind of quantum chip, we can do the very high precision quantum measurement, calculation, and even communication. Actually, this is the real occasion femtosecond laser should find use. And this is for the fundamental research. And industrially, we are doing we are doing and also sell the facilitated equipment for the cutting, drilling. Only if there's a requirement, always we are considering how to design the equipment to satisfy the requirements. Actually, we already succeed in several tens of examples. We will walk along such the direction. Yes.
Okay, great. Actually, Chris, maybe I can ask another question to follow up this. So HongBo, as a superstar, yeah, in science, I think you're really famous for, at least 20 years. So every year you have no result. What's the inner force, to pushing you hard working like this, think more like this? Because normally this was a big question for, now we're training many students. But some students say that, okay, I already finished my job. Okay, I can take easy. But like you, 20 years, go ahead, never stop. What's the inner force here?
Actually, it depends on different researchers. In my case, actually, I think a professor full of ideas is very important. So always, for each student, I should have some ideas to discuss with them. Actually, as you see, I demonstrate some applications, but it's really not so easy. In order to get new ideas, I read almost 100 books a year, and 1/3 of them are from different scientific field, and two-thirds of them from other field. I should by reading, I found during the reading, always I'm consider how to use my laser technology to your field. And then I think by this reading, I get a lot of many things are very exciting. and some of them now already assigned a task to students, and many of the ideas still in my brain. So my actual experience is reading is a very good experience to me. Yes.
Oh God, you mean 100?
Yeah.
Okay, yeah. So you got all my, yeah, well, yeah, everything here, yeah. I now know the distance. Yeah, I didn't read, more than 10 books. Okay, yeah, great. Yeah. So Chris, so we still have some time. Yeah.
Yeah, we still have a few minutes, no problem.
Okay, yeah, I can ask another questions. So, HongBo, I know you are long-term runner, right? Yeah, you do every day you're running, like 10 kilometers, you run for this for longer time. So can you tell us something, because many students here, how to keep energetic, how you do
Okay.
that?
Actually, I started running 10 years ago. At that time, I feel my health is already not in good status. Then I tried to walk fastly. Then just 1 month passed, I found my pain in knee, in neck already disappear. Then I found exercising is really good for health. Then I improved the stress of exercising, become from the walking to the jogging. Then at beginning, I consider just 1 week I run 4 times, 3 times, but always I can find some excuse to push the task to the second day. And I think this is not a good experience. Then I force myself run every day, no excuse. And even if it's very late, I do the running every day. I control the time 1 hour with the precision of plus or minus 1 second. I control the time, and distance should be more than 10 kilometers. If sometimes I just run slow, and then the total distance is smaller than 10 kilometers. Then I just delete the record and run once more. Then now if I see my record of running, it's really perfect. Every day, actually, it's 100%, no 1 day missing. And every day the time is 1 hour, distance longer than 10 kilometers. Force yourself to do something and don't escape.
Yeah, I couldn't agree more. Sport
Yeah.
is very good for both your body, but also for mental health. My hobby is really rock climbing, so I really try to do that 2-3 times a week. Yeah, so
Yeah, very good experience.
but 10 kilometers every day, that is respect.
But
A lot of respect.
recently, unfortunately, I have to tell you, recently I have some knee pain.
Problem.
Maybe the 1 day 10 kilometers is a little bit more than necessary. I think half may be good.
Well, this is maybe a nice way to conclude today's iCANX talk, or unless somebody still has an urgent question.
Yeah.
Okay.
No, thanks, Dan. Let me go to the last part of the event, because I think after the very nice discussion, I am more than happy to hand over this beautiful certificate that proves that you gave a talk here at the iCANX Forum. So congratulations, Professor HongBo.
Okay, thank you. Thank you, everyone.
Yeah.
And then I would just like to announce next week's event. We will have a contribution from Professor Osamu Tabata from Kyoto University of Advanced Science. And he will be talking about also a fabrication. Top-down meets bottom-up. way to explore plentiful room at the bottom. And I think early today we saw the same quote beautifully printed at the nanoscale. So thank you all and hope to see you all next week again. Enjoy your weekend. Bye-bye.
Okay.
Bye-bye.
Bye.
Yeah,
Bye.
great.
Nice weekend.
Yeah, that's
Oh,
great.
next weekend, huh?
Yeah, so
Bye-bye.
you are super, wonderful. So, yeah.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。能够像我一样飞越最高山岗。
ドローンによる宅配サービスが実用化目前です。ドローンに内蔵された TDK 部品の6軸モーションセンサーは加速度や気圧の変化などを高精度で計測、位置情報の正確さや強風の中での安定した姿勢保持に貢献しています。同時に通信データを送受信する場面でも TDK は独自の強みを発揮しています。Beyond 5G によって多数の機器を超高速かつ大容量で同時に接続させることが可能となり、データ通信のタイムラグはこれまで以上に小さくなります。その中核となる部品が TDK のアレイアンテナです。これは超多素子アンテナと呼ばれ、 約3センチ角の中に4096ものアンテナ素子が集積されています。 TDK はドローンや車の通信技術とビヨンド 5G を担う高性能アンテナ開発の両面から自動運転など未来の交通網の可能性を広げていきます。 Technology for the well-being of all people